Dr. Carlos Roithmayr is a senior aerospace engineer. He has authored or co-authored numerous refereed journal papers and a forthcoming graduate-level dynamics textbook. Dr. Haijun Shen is a supervising engineer at Analytical Mechanics Associates. He supports various aerospace engineering projects. His research interests include optimal control, spacecraft trajectory optimization, astrodynamics, control and estimation theory, and parallel computing.
Good afternoon. The title of our presentation is Dynamics, Control Design, and Challenges for Asteroid Capture. As Dan described to you, what we're trying to do is use a robotic spacecraft to collect an entire free-flying asteroid or a boulder from the surface of a larger asteroid. You don't see an indication of scale here on this picture, and that's intentional to get you to think of the object in those two ways, either as a small free-flying asteroid that will fit entirely within a capture mechanism attached to the spacecraft, or alternatively, this object is too large to fit in the capture mechanism, in which case we're interested in one of these boulders resting on the surface of the asteroid. So how are we going to capture this asteroid? What should our control strategy be? Well, one approach is to eliminate all relative motion between the spacecraft and the asteroid before capture takes place. Why might this be a good control strategy? Well, the thought is that eliminating all the relative motion gives you the best chance of avoiding damage to the capture mechanism and/or the spacecraft. Any asteroid that we can get to and bring back in a reasonable number of years is going to be classified as a near-Earth asteroid. That's what NEA stands for. And over a time interval of a few days, a good model for the rotational motion of an asteroid is that it is torque-free. In other words, there's no external torque acting on the asteroid. I'm going to show you three animations of possible torque-free motions of an asteroid modeled as a rigid body. And in each of these animations, you're going to see the spacecraft move according to the control strategy that we just discussed. The three animations show, the first one shows simple spin of an asteroid about one of its principal axes. The second animation is going to show an axisymmetric asteroid performing a combination of spin and precession. Axisymmetric means it has two equal principal moments of inertia. And the last animation is going to show you the most general possible motion for a torque-free rigid body, and that applies when the body has three distinct principal moments of inertia, and that motion is called tumbling. So let's look at the first animation. The rainbow-colored Easter egg represents the asteroid, and the colored box represents the spacecraft. As you can see, the asteroid is performing a simple spin about one of its principal axes, the z-axis, and the spacecraft has its axis of symmetry made to be collinear with the z-axis of the asteroid. And then it spins up to match rates with the asteroid, and it advances slowly in the direction of the asteroid. And just before capture, we remove that small translational motion so that there's no relative motion between the two. Next animation showing spin and precession of an axisymmetric asteroid. Now you can see that the rotational motion is more complicated. I should have mentioned previously on the simple spin, if we run into a target like that that's behaving nicely, we might classify that object as a cooperative object rather than uncooperative. So this motion is more complicated, and the rotation is different. You can see that as a result, the spacecraft translational motion has to be more complicated. It's moving around on the surface of a cone. But the strategy is the same. we align the axis of symmetry of the spacecraft with a line fixed in the asteroid and advance slowly in its direction until we can capture it. Now we can go to the last animation showing an unsymmetric asteroid having 3 different principal moments of inertia, and it's performing what's referred to as tumbling. That is the most general possible motion of a torque-free rigid body, and it's the most complicated. And so you see here the rotational motion of the spacecraft is equally complicated because it has to match, and then the translational motion that it has to follow is also the most complicated. So with that, I'm going to turn the presentation over to Haijun. He's going to describe 3 controllers to you. The first one takes care of the translational motion that you looked at. The second one takes care of the rotational motion that you saw in the animations prior to capture. And then the third controller he'll talk about takes care of de-spinning the combined object made up of the asteroid and the spacecraft after capture has taken place.
Thanks, Carlos. So, like Carlos said, I'm going to show 3 controllers that we have developed and used in our baseline study. The first one is the translational controller. As you can see from the video, our concept is the spacecraft approaches the asteroid along a line of descent that is fixed in the asteroid. And the motion of that line of descent depends on the asteroid angular velocities and attitude. We here assume that you can predict the angular velocity and attitude of the asteroid in the future, at least in the near future. So that requires us to have 2 more assumptions. That one assumption is to know the ratios of the principal moments of inertia of the asteroid, and also to know the angular velocity of the asteroid at some instant of time. These are very idealized assumptions. Carlos is going to talk about the challenges associated with identifying these quantities later on. So once you know the motion of the line of descent, we can design a desired trajectory along this line of descent, how you're going to approach the asteroid. And then you can design a controller to track that desired trajectory. And here we use a PD controller to track the desired trajectory, which is globally asymptotically stable. The second controller I'm going to show is for synchronizing the attitude. So the objective of this controller is to make sure that axis of symmetry of the spacecraft is aligned with the line of descent. We don't worry about the clock angle about the axis of symmetry because we assume that the capture mechanism is such that you can have a successful capture in any kind of clock angle. Again, we assumed the same 2 assumptions as before, knowing the ratio of principal moments of inertia and also the angular velocity at some time, t. The controller we designed is a combination of a linear feedback controller plus some extra terms. And here, U1 and U2 controls the transverse axes, and U3 controls the axis of symmetry. What's being fed back is the angular velocity error and the attitude error. The extra terms basically reflects the fact that our target is rotating instead of inertially fixed. And this controller, again, is globally asymptotically stable. The third controller is the de-spin controller. After the asteroid is captured or a boulder is picked up and ascended to a safe distance away from the parent NEA, the combined body needs to be de-spun to prepare for the next phase of flight. In designing that controller, we made 4 assumptions. First one is we assume that the payload is a rigid body, and then the spacecraft, of course, a spacecraft we assume it's a rigid body, and also the connection between the boulder and the spacecraft is a rigid connection. And we assume that we know the mass properties, like the center of mass and the inertial properties. And then we designed a asymptotically stable controller for the thruster throttles. So eta here is an n/1 matrix of thruster throttle, n being the number of thrusters. Then multiplied by this matrix F that gives you the 3x1 torque matrix. And R is a positive definite weighting matrix. In designing this controller, we have two objectives. One objective is to dissipate the kinetic energy as fast as possible. In the meantime, we don't want to spend too much fuel in doing that. So these two conflicting objectives are optimally balanced by picking this weighting matrix R. Now, as given in this form, this throttle, this controller, as given in this form, does not guarantee that the throttle stays between 0 and 1. And we found a condition such that under this condition, we can reconstruct this, this controller such that the throttle stays between 0 and 1 while maintaining the stability properties of the controller. All right. With that, I'll turn over to Carlos again. Thank you very much.
So, as you heard Haijun discuss, design of these controllers assumes that we know many physical parameters of the asteroid or the boulder that we're going after. And as you heard Dan discuss, there is some uncertainty regarding these objects. And so the reason for this uncertainty is that the objects we're interested in, the small free flyers in particular, are small. They can be dark, and they're typically very far from ground-based observatories, and they only come within range of our observatories for brief periods of time and infrequently. So because of this, we might not know that much about them. Another way to know about the physical parameters of the asteroids is that a spacecraft has been there before. So a precursor mission might help determine these parameters, but that takes time and money, and we may not have the luxury of a precursor mission necessarily for the asteroid retrieval mission. So let's talk about the physical parameters. In particular, there's mass. If the asteroid is large and has a non-negligible gravity field, then you can perform flybys, as you saw in Dan's animation, and determine the mass of the asteroid that way. If the asteroid is really small, such as one that's going to fit inside the bag, it doesn't have an appreciable gravity field, and in that case, you have to touch it and push on it with a known force to see how it reacts to determine its mass. So that makes it kind of late to be knowing what the mass is by the time you're already up there. The material strength, Dan also mentioned that we won't actually know whether this thing falls apart when we touch it until we actually go do it. So if that happens, then one of the key assumptions of our controller design is not valid, because we assumed everything was rigid and there was a rigid connection between the spacecraft and the asteroid. You've heard several speakers mention determining the angular velocity state. In order to do this, the object has to be close enough to a ground-based radar or to a spacecraft so that optical imagery can distinguish topographic features on the object. So that's hard to do ahead of time before the mission launches. Haijun talked a lot about inertia ratios. You can estimate inertia ratios to within a constant while it's undergoing torque-free motion, but in order to determine that constant and nail it down, you actually have to apply known forces at known locations to the asteroid. And again, that could be kind of late in the game, and your mission is already underway. The boulder mass properties, in order to know what those are, you have to actually move the thing around before you start your ascent, or if that's not possible, then you can start to estimate it while your RCS forces are being applied. But again, you're estimating the important physical parameters on the fly as you're ascending. And this will take a finite amount of time to be able to do. So these uncertainties in the boulder mass properties raise questions about robustness and control authority with your controller design. There are some other challenges that come up because the arrays are flexible and the manipulators are flexible. This drives you to not have a controller that reacts too quickly, but conversely, you want a quick reacting controller in order to avoid the arrays tipping over and possibly contacting the ground. And you saw mechanical push-off devices in previous presentations, and there's a possibility that when they push off, you may get an unequal application of forces from the three legs. So next steps to try to address some of these challenges would be to perform Monte Carlo analyses to study controller sensitivities to the variations in these asteroid parameters. And what we're hoping for from this audience are any ideas for robust control, adaptive control, or other ideas you may have. Thanks for your attention.